Hello to you. I am Sanjay NS, Master Trainer with the AIMS Teacher Training Program in Cameroon, abbreviated TTP Cameroon. Welcome to this third training unit entitled Networks of the fourth module entitled Mathematical Thinking and Problem Solving. In this training unit, we will focus on networks. Like the last training unit on combinatorial analysis and geometry, this training unit is not intended to give you university knowledge on networks. For reasons that we have already mentioned in previous training units and throughout this training, and which we wish to recall here once again, he who dares to teach must never cease to learn, according to John Cotton Dana, and he who ceases to learn cannot adequately teach, Gaston Bachard. By the way, if you are among us watching this video, it means that you are already fully aware of it, and we congratulate you for it. Teaching mathematics differently is only possible with you. Networks have been recently introduced into secondary education curricula in Cameroon. This gives this notion a special status, especially if we have never learned these concepts during our university training or have not really mastered it. The notion, therefore, represents a real epistemological and didactic challenge for you. As a mathematics teacher wishing to make the slogan "Teach mathematics differently" a reality, this is why this training unit aims to give you necessary tools to meet this challenge. We will particularly see how to teach networks by applying mathematical reasoning through an activity. And first of all, we will present in a general way the history of networks and its impact on the use of networks in our current society. In mathematics, the term network denotes an object representing a binary relationship, oriented or not, between elements of a set. A network is a set of objects called nodes or vertices that are connected together. The connections between the nodes are called the edges or links. Geometrically, we represent these elements by point vertices connected to each other by arcs of curves, otherwise what we call edges. Depending on whether we choose to orient the edges or to assign them a weight or a cost, we will speak of oriented networks or weighted networks. In mathematics, networks are often referred to as graphs, which must be distinguished from an alternative use of the graph to mean a graph of a function. The advent of networks is a conceptual revolution which shatters more than 2 millennia of geometry. In networks, the shape does not matter. That is to say, that all the geometric references inherited from classic Euclidean geometry becomes obsolete in favor of a single notion, that of the link between points. Since the beginning of the 20th century, this theory has been a fully fledged branch of mathematics. Since ancient times, it seems that representation of networks have existed. Just like Monsieur Jourdain and Proust, humans have been drawing networks for centuries without knowing it. Indeed, one can find at this period of the history of the drawings which one can very well identify with networks among the plays. A second representation has been widespread since the Middle Ages, and these are family trees. The family tree is oriented, although not explicitly, with the roots being a couple and the leaves being childless descendants. But if the drawn object looks like a network or even a particular type of network, it does not have the status of a mathematical object. It was not until the end of the 18th century, precisely in 1771, to encounter the drawing of a network whose purpose was to model a mathematical problem. This network was drawn by Van der Mon, who used it to illustrate a solution to the problem of moving the knight on a chessboard. The history of network really begins with the Swiss mathematician Leonhard Euler in the 18th century and finds its origin in the study of certain problems, such as that of the Königsberg bridges, the march of the rider on the chessboard, the problem coloring maps, and the shortest trip between 2 points. It was in the 19th century that the word networks was introduced by the English mathematician and surveyor James Joseph Sylvester. What therefore is the interest of network in the society? Network is not an independent branch of mathematics. It relates to linear programming, convex programming, topology, and even the calculation of probabilities. Beyond mathematics, network also finds several applications in the society. It is used, 1, in operational research for decision support, that is scheduling of tasks, project management, and logistics. It is equally used in optimization for technologies such as GPS, minimum cost, the shortest path between 2 points. It is equally used in transport networks, as in roads, in air transport, rail, and even electricity. It is equally used in IT, especially in programming to define data structures, in computer networks like the internet, and in other complexities. Like within the previous training units on combinatorial analysis and geometry, this part introduces how you, as a mathematics teacher, can develop mathematical reasoning and thinking in your students during a lesson on networks. The activity that we will develop will establish the relationship that exists between the number of vertices V, the edges E, and the regions or faces F in a simple network, also called the Euler's formula or the network's equation. To this end, the prime knowledge for this activity is the notion of a simple network, vertex, edge, region, and the ability to draw and recognize a planar and connected network. I invite you to follow along as you are doing the activity yourself. In this activity, we will use the following 2 networks. The first network in figure 1 represents the friendship between 7 individuals. That is Jala, B, Ngwa, Fe, Eposi, J, and Ya. The second network in figure 2 represents the road network between the administrative regions of Cameroon. For such activity to be successful, you must make these 2 figures available to your students before the activity begins. You have the following options for this. Either draw 2 networks on the board before starting the activity, or you could draw the 2 networks on a large sheet of paper which will be displayed in the classroom before the activity begins. Make sure that the content of the sheet of paper displayed in this way is readable by each student or by each group of students. Print the 2 networks on a sheet of paper along with the question to be given to the students or group of students. Before the activity begins, use a projector to project images before the activity begins. Students working together in small groups is the most recommended method, although this can be done individually. In order to make it easier for you to understand the activity and how each question can provoke reasoning and mathematical thinking in your learners, we have organized the activity into stages, where each stage is a question from the activity sheet to be given to each working group. Following each question, we explain the impact the question should have on the mathematical thinking of the learners. Let's take the following step as if we were doing the activities ourselves. The first step, that's step 1, list the vertices of figure 1. This instruction makes it possible to verify that each group of students or each student is able to identify a vertex in a simple network. This helps students to remember the notion of summit, that is, remember a prerequisite for this particular activity. The second step, step 2, we could ask the students to list the edges of figure 2. As with the previous instruction, this instruction makes it possible to verify that each student or group of students is able to identify an edge in a simple network. And the third step, step 3, you could ask the students how many friends are there in this network of friends. How many vertices V are there in figure 1. As you can feel, through these 2 questions, your students quantify the number of vertices for each network in figure 1. Step 4, how many vertices does figure 2 have? This question will allow you, your students, to count, quantify, and differentiate the different vertices of network 2. In the 5th step, you could ask them as well, how many edges are there in figure 1? How many edges are there in figure 2? As with the previous question, these two questions will allow your learners to count, quantify, and differentiate the edges of each simple network. In the 6th step, you could ask the students again, how many regions do we have for figure 1? How many regions do we have for figure 2? As with the two previous questions, these two questions will allow your learners to count, quantify, and differentiate the regions of each network. As you have no doubt noticed, the first 6 steps of this activity made it possible to verify that all of your students indeed have the necessary prerequisite for this activity. If as a teacher you ask these questions orally to the whole class and some students answered, you would not have checked the prerequisite at the level of the whole class, as we have just done in adding the questions relating to the prerequisite to be checked in our activity. Step 7. Record the values you got above in the table as below. The purpose of this instruction is to enable learners to gather information for better visualization. It is important that your activities have this type of instructions in order to instill this habit in your students, which can be used by them in solving an exercise. Step 8. For each network, add the number of regions R to the number of vertices V. Give the value of your sum. These two instructions allow learners to begin to establish a relationship between numbers. Step 9. For each network, compare the sum obtained previously to the number of edges. This instruction allows learners to begin to establish the relationship between the numbers of vertices, edges, and regions in a network. Step 10. For each network, compare the sum obtained previously to the number of edges. This instruction allows learners to begin to establish the relationship between the number of vertices, edges, and regions in a network. Step 11. In figure 1, what is the difference between the sum R plus V and the number of edges E? In figure 2, what is the difference between the sum R plus V and the number of edges E? Are these differences the same? Through these questions, your learners will be able to obtain the information necessary to establish the relationship between these different values. Step 12. What can you conclude about the number of vertices, regions, and edges in a network? Through these questions, your learners will conclude that there is a relationship between the number of vertices, regions, and edges in a network. Step 13. Write an equation relating these quantities. This instruction allows our learners to come up with the equation connecting the number of vertices, edges, and regions in a network. Step 14. Create a simple network yourself. Check if this relationship holds for this network. What can you conclude? These two instructions allow your learners to verify the obtained equation and to generalize to all simple networks. As for the previous training unit, we asked quality questions to guide the reasoning and mathematical thinking of the learners. During the activity, we were also able to check the prerequisite of the learners via questions that all the students answered. We invite you to use this strategy during your different lessons. It allows you to check everyone's understanding of your students, not just a few. However, at certain stages, your students may not be able to concretely answer the questions asked. In this case, since you are circulating among the students, you must prepare questions that will allow your students to get around this difficulty. Note that we have set questions and not answers. The quality of these questions will depend on the environment you find yourself in and how well you know your students. It is therefore important to know your students well. After the activity, we want to take note of these major points. Reminder of some definitions. The first one is planar network. A planar network is a network which can be drawn in a plane in such a way that its edges only touch at the ends. Connected network. Let G be the ordered pair VE, be a network. G is said to be connected if for any pair of distinct vertices V and W in the set V, there exists a path from V to W in G. A non-connected network is said to be disconnected. Another point that you have to take note of is a theorem, otherwise what you call it Euler's formula or network equation. Suppose that G is a connected network with region R or faces, edges capital E and vertices V. Then we can establish the equation V minus E plus F is equal to 2. In conclusion, we will never stop reminding you that as a maths teacher, applying mathematical reasoning and problem solving in your activities during your lesson is a must and even a requirement. Through this training unit, we presented an example of an activity applied to network theory. Although newly introduced in the Cameroonian curriculum, network theory cannot be taught without reasoning and mathematical thinking. Therefore, we appeal once again to you, to your leadership spirit and your dedication to enable your students to benefit from courses centered on reasoning and mathematical thinking. However, the activity we have proposed is not universal, which is why you should adapt to your students and your context. As you know, coming together is the beginning, staying together is progress, working together is success. Don't forget to share your ideas and questions in the forum. You can also go to the TTP-COP platform via the following link in order to discuss with the members of your cluster. Alone, we go faster, and together, we always go further. See you in the next training unit.